Okay, so yesterday I was trying to relate two very distinct processes. One is elastic scattering on a proton, The other one was actually deep inelastic scattering. So these are the two processes I described, and I tried to show that these two processes are related in some limit actually. Okay. How it is related, that is what I established. So this is what I did actually. So I initially started with, this is just a brief recollection of what we did. This is the momentum going in. This is elastic scattering. So we computed a cross section which looked something like this actually. I will try to improve the hand-filtering. Okay, so this is something which we first computed. Let me just write it down just to get a feeling of what it was about. Okay, I have written somewhere. So this is something like 4 alpha square E prime square divided by q power 4. I shift between small q and capital Q. This only difference is capital Q square is minus q square. So that's the only difference. So it shouldn't matter what I used. So this is 2m by q square cos square theta L by 2 delta 1 minus xpjyy. Okay, this is one part of the cross section. Okay, so and I said this. Okay, so let me just to make it a little more careful. Sorry. This is your first part. Yeah. Yeah. Yeah, sure. Yeah, I can actually move. Maybe you can bring the screen down to, up to that board or something like that so that. Okay, so the deep inelastic scattering cross section is, let me just put this as section. It's related to elastic scatterings. Okay, what are the elastic scatterings? elastic scatterings are basically on a point-like objects. So the pieces that appear here inside this two square brackets, okay, they correspond to a scattering on a point-like object. Assuming that the proton is a point-like, we could obtain a cross section which is proportional to two delta function. So I emphasize that you can see that actually the cross section on a point-like object, if you are looking at differential distribution, is proportional to a delta function. The delta function basically tells you the conservation of energy momentum. Rather, if more precisely, it was a delta function that was telling you about how this q square and p dot q are related actually. Okay? So nu was simply p dot q divided by m or whatever actually. So these two invariants were related simply by this relation. So elastic scattering, if you consider because of this energy momentum conservation, okay, you have a relation which is relating q square as well as nu, because as you simply see, you can p prime square equal to 0 implies p plus q whole square equal to 0, okay, which means this is, or p prime square is equal to m square, it is also related. So it is like a q square plus 2 p dot q equal to 0. So there is a relation between q square and p dot q. Okay. In the deep inelastic scattering, q square and p dot q are completely independent. Okay. So these are two independent, dot products or scalar products that now get related if you assume that this entire DIS is related to this elastic scatterings actually. So what is this, this small 1 minus xpj means actually? This factor basically means that it's exactly the same delta function, okay? Delta of, let's say, q square minus plus 2p dot q, okay, with p replaced by y times p, okay? So if you work out this delta function, q square plus 2p dot qy, you will get actually q square plus 2y into p dot q, okay? This equal to 0 implies that q square is minus q square plus 2p dot q into y equal to 0, which means if I pull out this p dot 2p dot q outside, okay, so you get this term which is minus xbj by y minus 1 plus 1. Okay, this is the delta function that you get actually. So it is in the delta function language, it is 1 by 2p dot q y into delta of 1 minus xpj by y. So it is basically the simple delta function tells you that the inelastic cross section is just algebraic sum of elastic scatterings on a point-like objects, and the momentum of that point-like object is fraction of the momentum of the proton momentum actually. That is all it means. So this simple manipulation by introducing a delta function in the deep inelastic scattering cross section implies that this entire deep inelastic scattering process can be thought of as a incoherent sum of elastic scatterings on point-like objects with momentum sort of scaled by the factor y. Okay, it is like if we have a proton, if you imagine that proton is broken into pieces as collection of point-like objects, and distribute the the momentum of the proton among all the constituents. Each one of them you give sort of without any bias, distribute it in some fashion. Okay, so the proton, pattern number 1 or whatever the constituent number 1 will get fraction y of the proton momentum. The other one will get y prime, y double prime, y triple prime, and so on and so forth. If you add all of them, the total momentum should be equal to the total momentum of the proton. So you distribute them actually. And this inelastic cross section is just simply sum of scattering on such patterns. Okay, each of them come with a very specific momentum fraction. Okay, so sum of all these cross sections is what we call actually DIS cross section. That is the kind of interpretation that people could bring out from simple manipulations. So all I did is actually just manipulated this DIS cross section and made it look like a sum of elastic cross section. Okay, having done that, okay, Bjorken and Feynman actually proposed an elegant model, made it more rigorous by making certain assumptions, and then said, let's not do this exercise every time. Let's make a one-time attempt to set up a picture, okay, that works only at very, very high energies, because this relation that I have discussed, it works when in a specific configurations. What is the configuration? The configurations are this, what we call Bjorken limit, the q square, that the momentum square exchanged here is very, very large, and then the p dot q, the dot product of this proton momentum and this photon momentum is very large. Fixing this ratio to a specific value. Okay, you don't keep it anything arbitrary. If you fix it as a finite value, then you have this picture actually. So this is a very special picture. A picture works in a very special situation. Okay? It may not work if you have a proton and then you sort of collide it with some low energetic objects. I don't think this picture will emerge. Okay, so this picture is works in okay. So the pattern model assumes that proton looks like a collection of point-like objects in a specific frame. Let's call this frame infinite momentum frame. What does it mean actually? This infinite momentum frame is a frame that the photon sees when this energy is extremely large, really, really large actually. Okay, it's simple relativity will convince you that if I sit on the photon, okay, and my photon is really, really going very fast, okay, and how would the proton sitting on a desk would look like actually? It would look as if it's moving in the opposite direction with very large momentum, right? So what is that frame? That frame is what we call actually infinite momentum frame. Okay, so instead of saying that you put a proton on a desk and accelerate this electron and hit, I can also reverse this process. Actually, you can actually think that photon is at rest. Of course, this photon is a virtual photon. In principle, it can be rest. Okay, and the proton is moving with really, really fast actually. Okay, such a frame is called the infinite momentum frame. Okay, so in that frame, okay, for an observer sitting inside on the photon will see proton not as a a ball moving. Okay, that's not the picture that it will see. What it will see for an observer at rest, the proton would look like a virtual state of a collection of point-like, okay, weakly interacting particles. Okay, so what does it mean actually? It is like, it's like taking a snapshot actually. Okay, so if I'm sitting on a photon, and then the proton is just passing by. For a moment, it would look as if I saw a collection of a state of partons. They are all in some virtual states. Okay, and that state will contain particles which are weakly interacting. Okay, I have to make this assumption that they should be weakly interacting, but it should be a collection of virtual particles. Okay, why? If I don't make that an assumption, then I don't think I will be able to explain this. Okay, so but we'll need to have some intuitive feeling of how this can happen actually. This can happen if you believe in relativity. Okay, relativity tells you that if you sit on a photon and then this proton is moving very fast towards you, let's say, then there's something called length contraction, right? There's a length contraction. That's something that you can see. Okay, so proton would not look like some spherical ball. It would look how it would look, some ellipsoid kind of thing. That is something that what I would see. Okay, the next thing that can happen is actually time dilation. Okay, so all the time scales that we are talking about are connected to the time scales related to the interactions. Okay, so the photon is going to interact with the proton. That's one time scale. Okay, that is completely decided by the kind of interaction that we consider, electromagnetic interaction. Okay, that's one time scale. And then the time scale among these partons. So we assume that proton is a collection of point-like objects which is moving. Okay, there is a time scale between time scale of interaction among the partons. Okay, so there are two time scales involved in this process. So one is the length contraction. Okay, other is the two time scales. Let's look at length contraction. What happens to the length contractions? So when photon comes in, hits the proton. Okay, if a ball gets shrink into ellipsoid, then the amount of time that it is going to spend inside the proton will be very less, right, when it interacts, because allowed spatial distance is small. So it can actually meet the proton, okay, and say hello only for certain time, because the amount of distance that it gets, the distant spatial distance, is very small. That's the role of Lorentz contraction. Is this clear? So it can't see actually proton for very long time. It will see only very little. I mean, it won't see the full proton. It will see only the contracted one actually. Okay, that's first point. Second, because of this time dilation, we'll have to see what is really happening actually. So if a photon comes, okay, and then the proton is going very fast, and there is time scale between these two. There's an interaction time scale, and then this states that the proton can have actually. There's the time scales. Okay, so states, when I mean actually, it is like when proton moves actually, there's a bunch of point-like particles non-interacting, but the way momentum gets distributed could be very, very different at every, it's like if you take a very fast moving camera and take a snapshots, it look like at one instance they will all be y1, y2, y3, etc. The momentum fraction, and then within a few seconds it will change to some other y1 prime, y2 prime, y3 prime. So the way it gets distributed. So this, if you can think of it, many snapshots of proton. Okay, so time difference between two such possible states is also important to consider. So when this when the infinite momentum frame, the time scale for the interaction to take place with one of the states, okay, is getting dilated, okay, in such a way that it does not know there exist other states when there's a collision actually. You understand what I mean? If you assume that the time scale involved between the time scale of the various states that you see in the proton is much larger than the time scale of the interaction, okay, then you will see that literally the photon will see proton as one state, some kind of a unique state. Okay, it does not know that there exists another state. Okay, so if there is a scattering, it would behave as if, okay, there's a bunch of partons came with a specific momentum fractions and interacted and went away. So that's the kind of picture one emerges if you assume time dilation, because there are two time scales involved in this process. Okay, so I hope it is clear actually. Okay, so this picture that Feynman and Abhay proposed is not very far from our imagination, because this is what relativity also tells you, that you can think of proton when the infinite momentum as a collection of point-like weakly now interacting collection of point-like objects, and the scattering can be thought of as independent scatterings because the time scales are different. Okay, so these scatterings are actually in some sense independent. This is against quantum mechanics, as you all know. Quantum mechanics does not allow amplitudes getting added up separately. There is also interference. Okay, so this interference between two different scattering amplitudes actually is suppressed in this particular kinematic configurations. Okay, that is why this in principle you should add all the amplitudes of individual scatterings. Okay, scattering of a photon on a collection of point-like particle. Okay, and then take another one, add all the amplitudes and square them, and you get squares of them and then interference terms. But here in this setup, because of the specific kinematics, and particularly this time scales involved between two possible states is actually very long compared to the interaction time. These interference terms gets washed up. Hence, you have a picture where you have a simply a sum of incoherent sum, almost like a classical scatterings. Okay, one scattering does not know about anything about the other scatterings. Okay, so that's the kind of picture. I hope I have sort of said quite a lot about this. Let me just write down the formula that what Partan model is all about. Okay, so any question? Okay, assume that, sorry? What is virtual state actually? So when I meant virtual state actually, I did not mean that actually this is I have some quantum field theory and then there's virtual particles and things. I meant, you can imagine that these are states that actually, of course you can probe, okay? It may not be a right word to use virtual in some sense, but yeah, how would I put it actually? You don't need to think of this as in a virtual state. Some states, collection of, it is like a snapshots where there's a bunch of partons, another snapshot, there's a bunch of partons. Here the distribution will be, each one will be y1p, y2p, etc., etc. Here it could be x1p, x2p, just like a snapshots. I call them as actually some states. Okay, very good. So, exactly. 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 Okay, thank you. So let's write down the formula. So let me just generalize this, okay? Make it more accessible to other processes too. So I switched from P dot Q and q square to xpj and q square. Because these two independent invariants, I can always write in terms of another two independent invariants. Okay, this is minus q square. Xpj is actually for your, this is q square by 2p dot q. This is same as q square by 2p dot q. Okay, so instead of writing down p dot q and q square, I've written this way. So this is the most convenient way of writing. This equal to sum over a integral 0 to 1 dy f at a. I'll explain what exactly I mean by these terms. D sigma hat p a of y x bj q square. Okay, so you can put whatever I said actually, that this inelastic scattering is sum of elastic scattering in one single line actually. Basically what it means is actually the deep inelastic scattering is related to elastic scattering. The sigma hat at EA is simply a process where electron hits a point-like object, okay, and then it goes. So this is a point-like scattering. The left-hand side is scattering on a proton, and then it breaks into pieces. So square of this, okay, I'm just giving you the square of this actually. This is also square of this sigma, d sigma hat. And what is this p, this momentum here, y? Instead of x, I have y. So y here is simply fraction of the momentum carried by this pattern of type A. So this is a scattering of EA going to EA. Okay, and that is multiplied with a function f, like a function, some function here f, f1 and f2 here. I'm generalized to one function for each pattern of type A. Okay, and this is analogous to this. So these functions are nothing but probabilistic interpretation for these functions are, these are nothing but probability of finding a pattern of type A in the proton carrying a momentum fraction y. Okay, that's the interpretation. So why this is probability interpretation? Because both d sigma dis or d sigma dEA are probabilities actually. These cross sections are the square of certain amplitudes summing over some kinematic configurations. Okay, they are probabilities. Hence, this has to be probability, and this is interpreted as the probability of finding a pattern with momentum fraction, finding a pattern, a type A, okay, and with a momentum fraction y. Okay, so and it is all summed actually. So you consider all possible patterns. If you have a pattern type A, you just put that. If it interacts, calculate the cross section, put it here. Multiply the corresponding pattern distribution functions. This is called PDF. Okay. Thereafter, I will use this word PDF, pattern distribution function. It describes about how the pattern shares the information about the proton. Okay, whether it's a momentum or spin or whatever, that in the school you will learn more about other aspects of proton that this function is going to carry actually. Okay, so this is the master formula I would call. Okay, this master formula was the one which actually would help us to calculate most of the processes, scattering processes that we need to compute in high energy physics actually. This is the master formula. This is the first master formula that we need actually. If I don't have this master formula, I won't be able to calculate any scattering cross section involving hadrons. So it's so important actually. So you better learn this. Okay. So this is how it is done actually. So you basically calculate this independent partonic cross sections each of them you multiply it with one probability distribution and sum all of them actually. And because that parton can carry an arbitrary momentum y, we need to sum them. So there are two summation involved here. One, the momentum fraction. Another one is actually the type of parton that participates actually. So you don't leave out anything in the cross section. Is this clear? Okay. So maybe I'll move to the other side of the board. Okay, so now you can start asking actually, can we extend this to some other processes actually? For example, let me look at, this is just a passing, but I will come back to this TIS and related topic. Okay, suppose I'm interested to do the following experiment. That means I want to calculate scattering cross section of producing two leptons in proton-proton colliders. Okay, you are all familiar with physics that is happening at Large Hadron Collider at Geneva, right? How many of you are? You all know that there is an experiment that is going on in Geneva, Large Hadron Collider. What that machine actually is one of the biggest, collider at present. Okay, I'm going to look at one particular process. Okay, the machine can produce all kinds of things. Okay, I'm going to look at one such, observable called, producing pair of leptons in the final state. This L could be anything, E plus E minus, mu plus mu minus, or anything. Okay, so I collide two protons, okay, head on, and then I produce one lepton here, another lepton here, and it could produce other objects also, let's say. Okay, so this process is called the Drelian process. Okay. Okay. This is the second process in this history of this pattern model that people could actually think of where pattern model can be applied actually. This because the kinematic configuration is also very similar to the DIS, hence one can actually calculate scattering cross section, using pattern model. So this collision takes place. Something happens here and then produce pair of leptons. So the cross section for example, I want to calculate d sigma by dq square, where q square is invariant mass of this by L plus L minus whole square. I want to calculate the cross section of this kind, d sigma by dq square of this final state. Then what would be the formula that I would write actually? Here we have two protons. That means a proton A can have a bunch of partons. Proton another, let's call this is proton A, proton B. So you can have two bunches of partons coming and colliding each other, producing this pair of leptons. Okay, so I wanted to have this picture in place here and write down a formula that actually can be useful for calculating the cross section. So Drelian cross section. Is this point clear to all of you? Clear? Okay. So note that because there are two protons, you need to have two parton distribution functions. Let's call this, let's say y1 integral ty2. Okay, let me just put x and it should be much more useful actually. So tx1 f a parton type A in a proton type A with the momentum fraction x1. Okay, this is something that is coming from the proton type A, and then you have tx2 fb pb x2. This corresponds to a parton type B with a momentum fraction y2 of the proton. So this parton A momentum is x1 times capital PA, and parton P momentum is x2 times PB. Okay. Now these two patterns now will collide. That's the picture that emerged from deep inelastic scattering experiment. Okay. So this product of these two functions is going to give you, two probability densities, PDF1 and PDF2, for a pattern type A and pattern type B, and the corresponding cross section for these two patterns A and B is given here actually. So this is the cross section where you have x1, x2 and q square. Okay. This is as simple as this actually. All you need to do is actually you calculate this cross section. This cross section is basically, there is a pattern coming here, another pattern coming here. Okay. With momentum PA, another momentum PB interacts and produce pair of L plus, L minus. Okay. This is what this means actually. So A and B. Now this A and B could be anything. Okay. So I need to sum all possible pattern types. So this is the formula that you can readily write down, okay, for computing hadronic cross section or producing a pair of leptons at LHC. So LHC you can analyze no data. Of course you can analyze the data, but you cannot actually interpret any of them without this master formula actually. You can produce, instead of pair of leptons, suppose I want to ask you the question that how would I calculate cross section for producing Higgs boson in Large Hadron Collider. All I need to do is actually I'll have to use a similar formula. Okay, pattern A coming from proton A, pattern B coming from proton B, and then they interact with each other, producing a Higgs boson. Multiply this, we'll get the cross section for producing this. Okay, so this is all about pattern model actually. I don't want to go into details beyond this point. Yeah. Heavy nucleons. No, this picture may not be working there actually. See this, because you're making the problem more complicated, so you'll have to break into pieces actually. First you'll have to consider how the nucleons are distributed among this heavy nucleus, and then you have to take a two-step process actually. But yeah, that also you can do it actually, but those are very difficult to measure. Okay, of course you can do that actually. That will make it more complicated, because if you are considering a situation where pattern not only in single proton, you are considering a collection of big nucleons. They will interact, of course. You will see that actually this picture is sorry? Very weakly. See, as a first approximation, you can do that. But, you will see that, the thing, the physics that I'm talking about is almost 50, 60, 70 years old, actually. There's some minute effects that, that I'm going to discuss more about it, actually. Okay. So this is the very naive picture, actually. You assume, assume quite a lot, actually. Okay. You'll see that actually a lot of improvements are required to actually make it work. Okay. I'm just giving a flavor of what pattern model means actually, how it came up in this context of DAS, and that how it helped us to actually write down such cross sections in hadron process. So this is a very important formula in high energy physics, so you better learn. Okay, so this is one application that I could think of in this context actually. Okay, I'll also give you another application using pattern model, how you would write actually polarized scattering cross sections. Okay, that I will come back a little later actually. So after this is clear to everybody, so everything transparent here. Wonderful. Okay, now I'm going to tell a few more things actually. Okay, those are very important because the F that I have written down here and the F that I have written down there Are they same or they are different actually? That is a question that one can always ask. For every process that I write down, I write actually what is the PDF, and then the cross section, parton level cross section. Okay, so let's now sort of register the names, record the names. This is called the parton distribution function, and this is called partonic cross section. Okay, so now in this exercise we saw that actually this d sigma hat Ea is calculable because it's an elastic scattering. Okay, it's not that you collide and produce a lot of particles. It's just elastic. Ea goes to some some E prime, A prime, or whatever. Okay, it's calculable. Okay, so let's list out things that that we can conclude from here. Maybe I'll write down all those here. So it's obvious that Ea is calculable because it is coming from a process of this kind. Okay, square of this process, calculating the phase space. Okay, it's calculable. Okay, what about here, this cross section? This is also calculable. Okay, for example, AB going to L plus L minus. It's calculable. So you express, hadronic cross sections in terms of some simple looking calculable quantities actually. Okay. So when I say calculable, I meant actually perturbatively. Okay, because I'm going to use perturbation theory that you learn in your quantum field theory course to calculate these cross sections order by order in perturbation theory. Suppose if it's a QED process, I will calculate in power series expansion of fine structure constant. If it is a QCD process, you'll see that you'll need to calculate these quantities as a series expansion in strong coupling constants. So they are all calculable perturbatively. Okay, perturbation really means actually strong interaction. It's a short distance processes because it is about scattering at very high energies. Okay, they're called short distance part of the cross section. So in some sense, these are called short distance. Okay, short distance physics in high energy scattering experiments. Okay, what about the second part actually, this F that I have written down here actually. F is basically tells you what is the probability of finding a parton with a type A with momentum fraction Y. Okay, and the same thing is what is interpreted here also. It is about a type of parton A in a proton A with momentum fraction x1. Do you expect they will be different or same as a distribution, as a function of x1? It should be same. So it will depend on only two quantities. One is what is the type of parton, A or B or C or whatever. Two, whether it's a proton or cousin of proton or uncle of proton or whatever. Okay, it depends on the target, which target that you are taking. If you have proton, it will have some particular distribution. If it's a neutron, it will be something else. If it is lambda, it will be something else, and so on and so forth. So it depends on what is the type of parton, what is the proton. Does it know anything about the scattering that we talk about? No, it does not know anything about scattering, whether this one is appearing here in deep inelastic scattering or in Brilliant scattering process. It does not care. So it's very, very special, as you can see. Okay, it has information only about the proton and the type of parton. Two, does not care about what type of process that one is studying actually. Okay, so in some sense, this F at A, x1, x, P, this PDF is process independent, but target dependent. parton type dependent. Okay. So it is a universal part of this entire physics program, right? It does not know which process you are looking at, which scattering cross section you are looking at, which lab you are looking at, where we are looking at, nothing. Okay. It's something very universal about that particular hadron. Is that correct? Sorry? Target dependent, because it depends whether it's a proton or a neutron. Okay. So it's a universal quantity. It is very specific to a particular hadron, okay, and a particular type of hadron. So it's a universal quantity, okay. And you can ask whether this quantity is calculable in the theory actually. Of course, you know, if you have the right theory, if you have a right mechanism, methodology to compute, you should be able to calculate actually. But you know, due to complexity of the theory, it is not very easy to compute. Okay, so presently they are not computable, you know, in a very easy way, in a very easy sense actually. Okay, so they are called, okay, so that's one thing. Second, because it is nothing to do with whether DIS and things like that. This is called long distance physics because it carries information about the hadron. Okay, it does not carry information about how energetically it is bombarded and things like that. So this the scales, the time, whatever energy scale that this function is to carry is very soft. Okay, in the distant language, it is called the long distance physics of hadrons. Actually, it is not about individual ones. Actually, so this entire process of this exercise shows you that the hadronic cross section actually factorizes into part which deals only with short distance physics and a part that deals only with long distance physics. So there is a separation of two scales in this particular kinematic region. So the Bacon limit is a very, very powerful, and it actually gives you this nice factorization of long distance and short distance physics actually. Because you can actually study in field theory in using what is called operator product expansion, the entire cross section, and show that Bacon limit corresponds to some short distance expansion, and this factorization takes place. So this is pattern model is just just a renaming of what we already know in quantum field theory called factorization or short distance expansion. Okay, so this is one thing. Okay, is this clear to everybody? Okay, having said that, I wanted to sort of get some nice physics out of it. Okay, because I'm running out of time.
Excuse me, may I make a comment here? I think that this is a crucial point, and there is an assumption that stays behind all these comments. Basically the factorization between events that happen on different energy scale and consequently also time scale. So the idea that has been described is basically can be summarized in one word: the factorization. And the idea is that whatever concerns the interaction with an external probe, this is high energy, and it becomes on a very short time scale because the probe itself is very energetic. So you just kick the partons in your target with this probe, and this is one thing. Then whatever happens to the structure, this is on a longer time scale. And also the pre-existing structure before the collision is something completely factorized. This is the assumption, okay? And this is what makes, that allows to describe these objects with two different techniques. So the interactions being a high energy, means a short distance, short time scale, can be computed with, you can use perturbation theory. which is the only technique we can have to make precise and rigorous calculations. All the rest is hidden in these pattern distributions, which are unknown, non-perturbative objects that must be deduced by comparing to the experimental data. Okay? I think that this is an important point that should be clear. Otherwise, I mean, you could get the impression that you do some tricks and magic. No, the assumption is this one, that because the probe is energetic, the collision is something at high energy, which is, happens separately, and then it doesn't interfere with the pre-existing structure, and also does not interfere with what happens after the interaction, where all the remnants of the target recombine and form the final hadronic states that in inclusive case you don't even observe. Okay.
Thank
Sorry
you.
for the interruption.
No, I think it was a very nice point, and it's very important actually. Yeah. Yeah, I mean, this actually, you know, whatever I said is about Bjorken limit here, just gets you a picture actually that, you know, there must be a corresponding, you know, very large energy limit, okay, where such, you know, assumptions can be made, and we can use the pattern model actually. So there is no corresponding Bjorken limit for the PP collisions actually. So for PP collision, there is no Bjorken limit actually as such. But the limits are actually that, you know, the proton A should see other proton in infinite momentum frame, vice versa actually. As long as you see that, you know, that the interacting particle sees the other proton, you know, very, very fast moving, then this picture will work actually. So energy should be very large, you know, that's the kind of thing actually. Sorry? Bjorken limit, yeah.
Since the broken limit itself is weakly dependent on Q square, so does this entire picture will be bit changed or it will be the same?
The picture will change. I will show you actually. This is a very naive picture that I discussed, okay, where there is a very beautiful, you know, separation of scales and things like that. You will see that how this scaling will violate it actually if I introduce interaction, because life is not so beauty like this here actually. Okay, you will see there are changes that we need to do. That's why I put cap here actually, okay, purposefully. Okay, so I will come back to this, you know, how this cap can be removed, what are the things that we can do, and make it more rigorous. I will come back to this. Here there is an assumption that I have made, okay, that patterns are free, non-interacting, nothing happens between them actually. That's not really what really happens in real situations, because you cannot go to Q square, go very large, or invariant mass in this case of trillion to be very, very, very large, okay, because these experiments are very specific setup actually. You can go to very large, but not to infinity, okay. So if you relax that, what will happen to this formula, I will explain to you, okay. Okay, let's assume that this, you know, this beautiful formula in the world exists, okay. Now, if I use this formula and calculate my structure function, xbj, okay, it would look something like this actually, because Bjorken said actually it scales as one variable. Let's see what that function is actually. So Bjorken only said it scales as one variable, okay. In this model, what is the result for this F1? Okay, what is the result? This is, if I calculate, assuming this pattern model picture, and think of this proton is made up of what actually? U, D, 3 types of patterns. Let's assume that what Kalman said was right, okay. So charges of these particles, F hat times A and proton. This is the result that you get actually, okay. You calculate F1 using this model, you find that it will be proportional to FA So you can just put that, A is equal to U, A is equal to D, corresponding charges. So it's just a sum of probabilities weighted by the charge factor is what we call F1. So the structure function that we actually wrote down containing the ignorance of the proton at very high energies now has a beautiful interpretation. W1 is not actually, W1 or F1 are not just some unknown complicated looking, some hypergeometric functions. They are simple distribution functions describing how the momentum of the proton is shared among the partons actually, okay? Particular about how U quark shares proton momentum, how D quark shares for proton momentum. So the structure functions W1 and W2 that I wrote down actually in the previous class, they are nothing but probability distributions of partons inside the proton. So this is the beautiful picture that emerges. I would call that an achievement of this entire program of understanding this deep inelastic scattering cross-section. Okay, now F2, for example, if we calculate, that also should give you some interpretation. One finds that it is just simply 2 times xbj times the same quantity, half of sum over u. Okay, let me just put this inside actually, which will make it a little more ud. 2 cancels. Okay, eq ea square xbj into fa np xbj. Okay, so this tells you how the distribution looks like actually. This F2 in terms of this distributions, and this looks like F2 is xbj times this. So if I have a probability distribution multiply the xbj fraction of the momentum, what does this mean actually? This tells you what is the probability that a particular parton has the momentum fraction xbj. Okay, it gives you the value of the momentum actually. Okay, so now if I know how to extract these quantities from the experiment, then I'm done actually. In fact, I can really tell quite a lot about how partons are distributed inside the proton, how the momentum distribution looks like, how much of U quark is there, how much of D quark is there, and all that information you can actually get it from these two functions. Okay, understand? So what you can extract is actually you perform the experiment. Okay, and use this formula. What this formula tells you here is actually half of 4 by 9 Fu in proton xbj plus 1 by 9 Ft in proton xbj. Okay, this is what you get. The second formula also gives you something like this with xbj multiplied here. Okay, now I do more experiments, and by some means I can have this F1 and F2 from the data. Using the data, I try to fit these two functions Fa and Fu and Ft and get some distribution actually. So you can get these distributions as a function of xpj. Okay, now if I get it, okay, what would I get from that actually? I can get many things. For example, let me just give you a few examples actually that what this objects can tell us about the proton. Okay, because this is supposed to contain information about the proton, partons inside the proton. So let's see whether we can say something about this. For example, if I calculate, let's say, integral dx bj 0 to 1, okay, xbj x is the momentum fraction. This is the probability at which parton comes with the momentum fraction x is the proton. So this tells you what it is the fraction of the momentum carried away by a parton A in the proton P, right? Okay. So if I sum all the partons, so this is more like fraction of the momentum PA by capital P, right? Now we know that if I sum all this A, it should give me what? Sorry? 1, conservation of momentum. So if I sum A here, what should I get actually? This is the probabilities. Okay, this is the momentum. So I just put capital P, multiply capital P, you get back this. So this is, what do you get here actually? Total sum should be 1, right? So these PDFs that you extract from the experiments from different flavors, okay, multiply each of them by Bjorken variable, integrate over all XPJ, sum all the partons, it should get actually momentum conservation result, which is 1. Is that correct? Okay, suppose I want to count how many U-type particle is there, how many D-type particles there in the proton. Can I use this F's to get actually? If these are probability distributions, you can get, of course. So proton, when I said it's 2 U-type, it's actually 2 U valence quarks, which is defined as U minus U bar, like this. Okay. So this is the difference of this. So valence quark by definition means actually that it's the difference between the PDF for U and PDF. I'll stop in 2 minutes actually, I'm almost through. Okay, this is the valence quark distribution. So now if I want to find out that what is the total number of U-type valence quark inside the proton, what is the total number of D-type valence quark in the proton, the only way to compute is actually calculate this quantity Txpj, okay, F of U in proton minus F of U bar in a proton, okay. Forgot to add, everything you have to add, right? Because proton can have an antiparticle actually. Okay. Only naive, if you make an assumption that proton contains only particles, then this is a pattern model, it's not quark model. Okay. It can have any number of, any kind of particles actually. Okay. This also explains the word virtual, and I said actually that you may not see U bar, but U bar can exist as a pair of U bar. Okay. So okay, fine. So this is, you multiply this and calculate this quantity. So what is this number will tell you? This number will tell you, this is a number, okay, because if I integrate this total probability, it will count the number of U type of valence quark, okay. So this number has to be equal to 2 because proton has 2 U quark. So this is the relation that you get. Similarly for D quark, okay, D valence quark, F of D in proton minus F of D bar in proton, if I calculate, this should be 1, okay. So these are the relations that you can get from the PDFs that we extract actually, okay. It is, in practice it's the other way around because these PDFs are extracted from experiments. Often one imposes this kind of a constraints to actually fit the functions actually. So PDFs are not calculable, they are actually extracted from experiments by measuring this structure functions and fitting it against this nice looking formula. You extract this distributions actually as a function of XPJ, okay. And these all these distributions satisfy certain relations. These relations are called sum rules actually, okay. Sum rules are basically rules that we obtain by using some model for proton. If the proton is collection of type of particle that we talked about, 2 valence U quark and 1 D valence quark, then that's proton, and neutron also you have something like that actually. So you can go on and try to extract these functions. And because they are universal, okay, you can extract from one experiment and use it for other experiment. For example, from deep inelastic scattering experiment, you can extract the PDFs and use it for proton-proton collisions or proton-antiproton collisions and things like that, because they are universal quantities. So I'll stop here and continue probably.